Hi, my name is Alexander Savage, one of the architects on the Coherence engineering team. In this presentation, I will talk about new asynchronous name cache API that was introduced in Coherence 12.2.1. In the first part of this presentation, we will cover the reasons for the introduction of the Async API, as well as Java 8 features that allowed us to implement it, completable future. We'll then briefly discuss asynchronous entry processors and aggregators, the low-level building blocks that the Async API is built on. And once we have the basics covered, we'll look at the Async name cache API, and I'll run a demo that shows performance gains for basic operations that we were able to achieve by adding Async API to Coherence. We will then take a look at another demo, which is much more complete application, web crawler, and compare and contrast asynchronous implementation of the crawler, which will not only highlight performance differences, but will also show you how easy it is to write asynchronous applications using Coherence, Async API, and Java 8 completable future. In the process, you will also learn how to implement an HTTP proxy on top of Coherence in less than 200 lines of code. So let's get started. So the first question is, why did we decide to implement Async API? The primary reason for the addition of Async API is increased efficiency. Many Coherence applications unnecessarily block application threads when performing basic operations such as gets and puts, simply because writing correct multi-threaded clients using synchronous API is too cumbersome. The combination of a proper non-blocking asynchronous API and Java 8 completable future makes the implementation of non-blocking Coherence clients much easier and allows us to achieve some truly monumental performance gains, as you'll see in a demo in a bit. So let's talk about completable future for a second. If you're not familiar with it, it is one of the major new features of Java 8 that ended up somewhat under the radar and didn't really receive nearly enough attention, mostly due to popularity of other Java 8 features such as lambdas and streams. And while popularity of lambdas and streams is very much deserved, completable future is also a very powerful new feature. What completable future does, unlike standard future interface that we had for a while in Java, is actually it enables easy compositions of asynchronous tasks. So it's not just you submit work for execution, then you can either let it go or block on it, such as calling future get. With completable future, you have a number of methods that allow you to compose multiple completable futures, and they all return a new completable future. So for example, you have static all of and any of methods. So you can pass an array of completable futures to both of these methods, and they will give you a future that completes when either all of the futures in the array or any of the futures in the array is completed. Then you have methods such as then accept, then apply, then combine, then compose, then run, when complete, handle, which are different variants that allow you to execute a piece of code or to apply a function to the result or to compose multiple, to turn asynchronous execution into sequential execution using then compose, for example, etc., etc. The initial completable future can be created from a runnable or supplier. There are static factory methods that allow you to do that on the completable future itself. And as you'll see later, Coherence API gives you a really easy way to get completable futures, because basically all the methods on the async name cache API return completable future. This is brief intro, but you can find a really good introduction to completable future at the link provided on the slide. So if you're not familiar with it, I definitely suggest that you take a look at the tutorial that is available on that URL. For now, let's look at a couple examples. In the first example, we're basically creating completable future. The goal of the example is to fetch a page from a specific URI and then process the page. When we say process the page, it means parse the page, find all the links in it, and go fetch those links recursively. and do the same for all of them. So in this case, we are creating a completable future that starts by fetching a page from a specific URI, and then once the page is retrieved, it calls process page method that does parsing and processing of the page. In the second example, we do the same thing, but we actually do it not for a single URI, but for multiple URIs. So we have a set of URIs, we create stream from that set. And then in the first map stage, we create completable future, just like in the first example. We create a completable future, supply async, and then we provide a supplier that calls fetch page for a given URI. And then in the second, this stage basically returns a new completable future, right? And then in the second stage, we call then compose on that page future and call process page on it. So it's exactly the same code that we have in the first example. And then finally, because we are now processing multiple things, we will have multiple process page futures. And we convert those to array using to array completable future : new. And then finally return completable future all of tasks based on the array that we created. So this gives you a really easy way. Combination of completable future and stream in this case makes it really easy to process number of tasks and to combine them using completable future all off into a single future that you can then wait for or add some more and compose some other tasks on. So that's as far as we'll go regarding completable future. So now let's look at some of the building blocks that Coherence provides that allowed us to implement Async API. The first of those is asynchronous entry processors, which were introduced in Coherence 12.1.3, but were significantly improved and extended in Coherence 12.2.1. In addition to asynchronous entry processor that handles multiple entries at a time and is basically used with invoke call, we now also have single entry asynchronous processor, which is used with invoke and is used to process a single entry. So things like gets and puts will use single entry processor, while things like get all, put all, etc. will use asynchronous entry processor. And then finally, we also have streaming asynchronous processor, which doesn't really return anything, but basically gives us a way to process individual results as they stream back. So instead of getting a map of results, as is the case when you do invoke call with a regular entry processor, you will basically just get a notification that processing is complete. And in the meantime, you will get individual entries for each of the results that would be in the final map. Asynchronous entry processor can be easily converted to completable future now. Basically, if you execute a code in this example, you basically create an entry processor, you call cache invoke on a key passing the processor in, and after that call is made, you can basically call async get on the processor itself. You can call get completable future method and it will return completable future, which might or might not be completed already. So once you have that completable future, you can do anything you can do with completable future, compose it with other futures, etc. The second building block is asynchronous aggregator, which is new in 12.2.1. This is something we've added to complete the foundation for the async namecache API. And just like entry processor, it can also be converted to completable futures. If you create an instance of it and call cache aggregate method with it, after that you can call get completable future on it and you will get completable future back. Both of these low-level features, entry processors and aggregators, can be used directly, but there is rarely a need to do so. I'm sure you'll agree once you see the examples that the higher level async API that we implemented on top of them makes our life much easier and makes the implementation of async applications on top of Coherence much simpler. So let's take a look at the Async API and then we'll move on to the demos. As I said, the Async API is new in this release. It's introduced in 12.2.1 and it is built on top of async entry processors and async aggregators, but it makes operations much simpler. So instead of you having to create instances of appropriate entry processors and get completable futures from them, you can simply call cache.async on your standard name cache that you're already familiar with. You can call this new async method, and then you basically have most of the methods that you have on the name cache itself. So you have methods such as invoke all, aggregate. You also have methods such as get, put, remove, get all, put all, etc., etc. Pretty much all the methods from the name cache are available on the async name cache with few exceptions. The major difference between these calls and the calls on a standard synchronous name cache API is that all the methods on the async name cache return completable future. So that allows you to compose asynchronous operations easily. Once you call the method, you get completable future back, and then you can merge it with other completable futures. You can block and wait for it to complete, etc. So you don't have to create completable future yourself. Basically, any operation on async name cache API will create one for you that you can use from that point forward. In addition to that, as I mentioned earlier, we provide a streaming API. All bulk read operations such as get all, entry set, key set values, as well as invoke all, also have the streaming variants. And those usually come in two shapes, depending on what we are returning. So for get all and entry set, for example, which return map entries, you will see these two variants. For key set and values, there will be only one, because they only return one thing. So the first variant basically allows you to specify a consumer that will be called with a map entry that contains key and value for each result of the get all operation. And the second variant allows you to specify by consumer, which basically also gets key and value, but it makes it a little bit easier to code against if you don't need map entry itself. So we provided both of those, and the main reason for the streaming API in general is to basically allow you to consume a stream of partial results without collecting them on the client or on the server for that matter, because if we are streaming results back to you, we know we don't need to collect them. It's going to save some memory on the server, it's going to improve performance, you're going to get the results on the client, process them without ever having to collect them into local collection. And all of these methods, as you can see, return completable future void, because there is because we are not collecting, we have nothing to return really. Once we have called the callback for each of the partial results, the only thing that we do is complete the future that returns nothing, just to let you know that we are done, that there is nothing more. And at that point, you have the future that can be used to compose. That can be composed with other futures. So let's look at the first demo, which shows some basic get and put performance differences between synchronous and asynchronous API. So I have two cache servers already running, and I'll start a test because it will take a minute or so to run, and then I'll walk you through the examples. So while this is running, these are basically our tests. We're doing test for asynchronous put. This is the test. We create an array of 1,000 completable futures. We will do 1,000 individual cache async put operations. And what we are putting in is this binary, which is created here, which is basically just a 1 kilobyte big binary object. And then we'll run this test 100 times and report the results. So it will do 100 iteration warm up, and it will run the test itself 100 times and time it and report average for the 100 runs for the test itself. Keep in mind that the result that's reported is actually for 1,000 asynchronous puts. And the same thing for synchronous put. The code here is very similar, except we don't have to do anything with completable futures. So the code is do 1,000 synchronous puts in a loop. and then same thing, we run it 100 times, report the results. Similar thing for asynchronous get. We have completable futures, we run it 1,000 times. We wait for all futures to complete to make sure that we are not reporting results for things that haven't completed yet. And we do the test. And similarly for synchronous get, populate the cache, define the test that we want to run, and run it 100 times. So this is basically what do test does. It will run the warm-up loop, it will run the actual test loop, and then report the duration that it took per iteration, and the throughput in thousands of operations per second. This takes into account that we are doing 1,000 gets or 1,000 puts in each iteration. So let's take a look at the results. As you can see here, synchronous put took almost 200 milliseconds per iteration, and which gives us about 5,000 puts per second. Asynchronous put, on the other hand, took 27 milliseconds per iteration, or 37,000 puts per second. Synchronous get, 100 milliseconds, or about 9 to 10,000 operations per second. Synchronous async get, 22 milliseconds, or 45,000 per second. And the results will be slightly different based on each test run, but in general, async get and put both are around between 20 and 25 milliseconds, and sync put is about 10 times slower, about 200 milliseconds, and sync get is about 5 times slower, about 100 milliseconds. So those are the results that I was getting fairly consistently, even on much longer runs than this one. So let's switch back, and basically that's what this table captures. We're doing 1,000 individual gets or puts with 1 kilobyte object using 1 test client, 2 cache servers on my laptop, which is 2013 MacBook Pro with Core i7, 2.7 gigahertz and 16 gig of RAM. And the results that I got on the particular test that I used to capture information in the slide, I had this is divided by 1,000 for the 1,000 individual gets and puts. So I have 94 microseconds per get, or about 10,000 gets per second, and about 200 microseconds or 5,000 puts per second for the synchronous API, and then 22 microseconds or 45,000 gets and puts per second for the asynchronous API. In this case, both took about the same amount of time. So as you can see, we're doing the asynchronous gets are about 4 to 5 times faster than synchronous gets, and asynchronous puts are about 9 to 10 times faster than synchronous puts, which is significant improvement. So let's look at a second demo, which is actually a lot more fun than just comparing the numbers in the test. What I did here is we still have the same 2 cache servers running, and we will load some data into them. And basically what we will load is the content for the coherence.java.net website. So this is Coherence community website. It provides links to a number of sub-projects, open source projects that are related to Coherence that many Coherence customers use and rely on. It also has links to Coherence on main Oracle website, as well as to individual projects on GitHub and java.net. Finally, it has all the events, upcoming past events that we do like Coherence special interest group meetings, as well as an archive of speakers and past presentations. So It has, what's nice about it is it has quite a bit of content so that we can download. For example, it has all these presentations linked as PDF files. So our crawler will have something to do. So it will have to download all the HTML pages, all the style sheets, all the JavaScript files for the site itself, plus all the PDF files that the site is linking to. So let's run the crawler. And first I'll run, I have two implementations of the crawler. One is synchronous, which does everything using old synchronous API and effectively makes the whole thing single-threaded throughout the process. And then we also have the asynchronous crawler, which takes the advantage of the Async API and tries to use cluster resources as much as possible. So let's run the sync crawler, and as you'll see, the first thing it will do, it will clear the local cache, and now it's starting to fetch different artifacts. And if we look at the cache server, you will see that both cache servers are fetching different content objects. So while this is crawling the site, and it will take a while, it takes about 2 minutes for it to finish. Let's take a look at how this whole thing works. So first we have Coherence cache config, and in this particular case we have web cache scheme, which stores object with string keys and static content values. And if we look at a scheme for this web cache scheme, you'll see that it runs with 10 threads. It is read-write backing map scheme, and it uses this HTTP cache loader for the given cache name. This cache loader is basically allows us to do read-through. So when we do get request on a cache, it will, if the object is not already there, it will go and fetch it from based on the domain and resource name it is configured with. So for coherence.java.net domain, it will go to the resource that we specify, and we have coherence.java.net defined as a cache name. So what it does is it basically uses a Jersey client to simply make a GET request to the target URI. If the status is 200, it reads the binary, it logs on the server that it succeeded, and this is how many bytes the content is, and it creates a new static content instance with the content and the media type of the content. And that's basically all there is to it. And it's actually very, very simple. We also have, in order to serve this, we have, going back to the config, we have proxy scheme that defines HTTP acceptor and defines web server, REST Jersey application, web server application as a root application in the context. So this web server is actually just as simple. All it has is a single endpoint which all the requests go to, and basically gets the domain name from the endpoint as first part of the path, and then after the domain name it gets the endpoint gets the name of the static resource, defaults to index HTML if it's not there, and then it just fetches gets the cache, gets the static content based on a path from the cache, and if the content is null, returns 404, not found. Otherwise, it renders the content back to the browser. So that's really all there is to it. And all of these three classes are about 180 lines of code or so, and are effectively implementing an HTTP proxy on top of Coherence. So going back here, we can see that the server is finished. They're not doing anything anymore. The crawler finished, and it took about 145 seconds for it to do its job. And the reason it took that long is because it was really doing everything synchronously. It would go and fetch the page, then on the same thread on the client it would parse the page, get the links that the page points to, and then go to each link individually one by one and do the same thing, process them, parse them, etc. So even though we have 2 cache servers and 10 threads on each, which means we have a total of 20 threads, we were never using more than one at a time. So the client was effectively single threading the whole application, even though server had a lot more resources that it could use, because server could fetch many of these assets, many of these resources in parallel. So let's do the same thing with the async crawler. And the first thing async crawler does, just like the sync crawler, it will clear the cache to make sure that it loads all the resources again. So let's run it, and as you'll see right away, it will print out everything much faster. Now, this is not finished yet, right? I mean, it actually made a request, it parsed all the content, it made a request for all the resources that we need to fetch, and the servers are still working on fetching those, right? And you can see the servers are actually working faster than before, and that will be reflected. And now we are done. An async crawler is done, and it took about 24 seconds. So 145 versus 23, and the code is very much alike, and the functionality is exactly the same. So let's take a look. It's actually going to be easier to do it in the slides and just focus on differences between synchronous and asynchronous implementation of the crawler. So starting from the top, the first line that you have is basically what you would have in your main method. In this case, we just create a new instance of a sync crawler for a given domain, which is coherence.java.net. And we call a crawl method with the root URI, typically index.html. The crawl method will fetch the page for the root URI, and once that's done, the fetch page is recursive method, so it will fetch, process. Once it parses all the links from it, it will call itself recursively and fetch other pages, etc., etc. So once fetch page is done, we will have cache populated, and we can return cache size to get the number of objects, number of resources that we crawled from this specific URI. The bottom example is the same thing implemented using Async API. So we're creating async crawler. We're also calling crawl method with the root URI. And the only difference here is that on this crawl method, which, as you can see below, returns completable future instead of int, we're calling join because we want main to block until this crawler completes. So the crawl method itself calls fetch page, but now fetch page also is not just a method that is void, that returns void. It is a method that returns completable future as well. And when this fetch page method completes, we are calling then apply async and also return cache size. We have to do it asynchronously here because we are making synchronous call to the cache size method. So in order, coherence requires you cannot mix asynchronous and synchronous calls. So if you want to make synchronous call, you need to make sure that it's executed on a different thread, which is what then apply async ensures. So let's look at the fetch page method in both cases. So synchronous implementation on top basically just calls fetch resource for a given URI if the resource is not null, because we need to guard against cases when the request might return 404. We might have broken links in the page. If the page is not null, then we call process page with the retrieved static content. Similarly, for the async implementation, we call fetch resource, which again returns completable future. Once that future completes, we will call, if the page is null, we will return completed future, which is just a convenience method on the completable future itself to return future that is already completed in case of broken links. Otherwise, if we did get a page, then we will process the page just like in the previous example, and that will return completable future again. So looking at the fetch resource method, the first one is very simple. We're basically just calling get on the cache itself, and that will trigger read through to our cache loader, which will go and make requests to the Coherence Java.net to fetch the appropriate HTTP resource. And then in the second example, I'm actually using, for illustration purpose, I'm using, instead of doing async get, I'm just doing async invoke on the URI and passing single entry asynchronous processor, just to illustrate that you can actually do a couple of things that you cannot do using just a high-level API. What low-level API, such as single entry asynchronous processor, allows you to do is specify not only the entry processor, as in this case, map entry : get value, but also whether you want flow control enabled, which is true by default, so we're just repeating that. And finally, the order argument, the order affinity. And this last argument is important because Coherence actually ensures ordering of the requests. By default, it will ensure that the requests coming from the same client thread are executed on the same server thread. So by default, you will have ordering between different client-side calls, even though you're using Async API. This is very useful, for example, when you're doing gets and puts, because those are cheap operations. Those are simple and cheap operations that tend to perform best when they're executed by the same thread on the server instead of by switching threads, because the cost of context switching is too high when the operation is cheap. On the other hand, we have expensive operations here, and we don't want that behavior. So I'm actually overriding default behavior here by changing thread ID that would be used normally to the hash code of the URI itself, which will ensure that it will be different basically for each URI that I'm trying to invoke. And that will allow this code to actually execute on multiple threads on the server. So instead of executing each request on the same thread on the server, this will allow it to execute on different threads on the server. And finally, we have process page method, which again in a synchronous implementation receives static content. It uses helper method to get local URIs, which actually uses JSoup to parse the HTML and get the list of links from it. It filters the links, etc., etc. So in the end, what we have is a list of URIs that we do want to download. And then for each of those, we basically check if it ends with HTML. We call fetch page recursively and process it just like the original page. Otherwise, we call fetch resource to simply get the resource and load it into the cache. We know that there is no additional processing that needs to be done to it. And the implementation, the asynchronous implementation, is actually quite similar. We get the same thing, local URIs from the page. We have a stream of URIs. The first map operation does the same thing that we did in the if statement above. If the URI ends with HTML, we call fetch page, fetch resource. Remember, in this case, in the async implementation, fetch page and fetch resource both return completable future. And then we collect those completable futures into an array and return completable future all of tasks. And that basically gives us our full implementation. So basically what happens in the async implementation is for a given root URL, like index.html, we will create a tree of completable futures for all the linked pages, CSS files, etc., etc. And we will wait for the root future to complete, and root future will complete once all of the nested, all of the child futures in the subtree are completed. So as you can see, yeah, it is a little bit different than doing things asynchronously, but it is not that much more difficult, and the performance benefits are definitely worth it. And just to show now that we actually have this page working, this is the original site, coherence.java.net, and now let's see what we have locally. So let's 8080. So here is the page loaded from Coherence. And we can go to events. It's all there. We can go to speakers. It's all there. And let's look at some presentations. And this should actually be much faster with Coherence because we have everything locally. And as you can see, opening PDF is instantaneous. And if we do the same thing here, well, it might take a while. As you can see, we're basically serving localhost 80, coherencejava.net presentations, and we are effectively proxying the Oracle Coherence community presentations page. Which brings us to the end of the presentation. As you could see, Java 8 Completable Future is really a great addition to the platform. It enables very easy composition of asynchronous tasks. It is much easier to use than any of the concurrency constructs that we had before Completable Future was introduced. It is somewhat underrated and out of spotlight because of lambdas and streams are so popular and took most of the publicity after Java 8 release. But it is very, very powerful feature. Coherence 12.2.1 adds completely new asynchronous name cache API that is based on combination of completable future and low-level features that Coherence itself provides, such as asynchronous entry processors and asynchronous aggregators. And as you could see from the examples, it is much easier to use than if you had to use low-level features directly. Bulk read operations also support streaming mode, which gives you better performance and reduced memory usage on both server and the client. I hope you enjoyed the presentation and you will enjoy using the Async name cache API in your next application. Feel free to post any questions or feedback in the comment section for this video, or reach out to us via one of the following social media channels. Thank you.